last class first, summarize that. So in last class, we discussed that for all electrical equipment, whether it is a generator, whether it is a motor or it is inverter or converter, transformer, whatever may be, the higher power rating electrical devices are usually, as a rule, you can say, as a rule, are high power, high voltage rating devices as well. But that means if your power is higher, the optimum voltage is also higher. This is because the same rule applies that conductor cost reduces with voltage, whereas the insulator cost increases with voltage. But it's not necessary that always this insulator cost will be look like this. In some cases, say for example, if insulator cost will be look like this, then obviously economic voltage or optimum voltage will be lower. So these two, I can say that this trend may be for transmission line, if then this trend may be for generator in general. So what I mean in summary is, the for each and every equipment, higher will be the power rating, higher will be the voltage rating as well. However, this high voltage rating varies from device to device or equipment to equipment. So for a generator, this voltage rating for optimum voltage for the generator is lower than the transmission line, and this is mainly due to the insulation cost and overall size of the, I have discussed with you in detail in last class, so just remind you. Then we also discussed that the when we interconnect the several lines into form a grid or power system, it might be thinking that yes, we can add the only the same voltage lines together, and so, no, that may not be the true. So each and every transmission line or links in the grid can be designed and constructed optimally for their voltage rating based on their how much the power they are transporting and to up to how much distance, and then if necessary at the interconnecting point this voltage again can be converted to have a common voltage at the interconnection point only. I have shown you that example also. Then we discussed that in a power delivery system, we have one part called transmission. Now, by now, you might have been a little bit aware about what's the transmission and what's the distribution. So, basically, the distribution system receives the power at the transmission level. So, that means we have a grid. So, these grids may be connected, look like this. So, in general, the distribution system started from this point, or it may start from this point, where in this grid, the several generators are connected and the several lines are connected. So, we even it is a radial this distribution system. We cannot say that we are receiving without analysis that whether we are receiving at this junction the power from this generator, or this generator. Then we also discussed that even within the distribution system, we may not have only a single voltage level throughout, but from section to section or from level to level, the voltage may be different. And this voltage is converted by some substation in the distribution systems. And basically in distribution system, we have two voltage conversion. One is called area substation, where the voltage is converted from sub transmission level to primary distribution level, and very near to the consumer, this voltage again is converted from the primary distribution voltage level to the secondary voltage level or utilization voltage level. So that transformer we call as distribution transformer. So distribution transformer change the voltage to the utilization level for retail customers or very small customers. Then we had discussed so many things, but more importantly, from the design point of view, we discussed that how we can distinguish the transmission line design and distribution system design, as transmission line design is a top-down approach. What does it mean? That we start, say, for example, from here at this point, and now say we say that how much power we may need to fed or evacuate to this grid from this generator. So a starting point is how much power has to be transported at how much power P has to be transmitted over how much distance. So that's the basic part criteria or basic philosophy for the transmission line design. However, for the distribution system design, this approach is exactly reverse. So that means in the distribution system, what will happen that why you are doing the distribution system? To feed the power to the consumers. So that's why you must know that who is your customers, who is buying your electricity, for what purpose, in what amount, and then you start from that. So the starting point for the consumers is for the distribution system is the consumer. So we may have the consumers at the different places. So these are the consumers, suppose. So now you have to first starting point this, then you may calculate that how much will be the power required for all these consumers. Then you will set up that if I put a distribution transformer over here, how much capacity this distribution transformer will be needed. Then from this distribution transformer, what is the optimum way to connect this distribution transformer from the primary distribution system, and then how this primary distribution is ultimately coming from the substation. So that means it is just a reverse process, that is bottom up approach. So we go from the very bottom level, consumers, towards the source. So it is from consumers towards the source is the distribution system design, whereas in transmission system is top down approach, that is from the source to where the power has to be delivered. Okay, so then we discussed that, yes, in the transmission line design, what we are going to discuss in this course. Yes, so the base I will go one by one in this course, all these parts. So just in summary, I will recall you that we have discussed basically the 5 steps by which we complete the transmission line design. And these 5 steps includes, first step is selection of the voltage level and number of circuit in repeated times. Now I have explained you that we should select the voltage level and number of circuit together in an optimum manner when we start the transmission line design based on the economically and technical requirement. Then we also discussed that we will going to discuss these things. In fact, 2 to 5, we are going to discuss each and every one as a chapter itself. So I'm not going to discuss again this right now. So we start from this one, the very first one, that is how to select the voltage level and number of circuit economically. In fact, as some hint I have already given you also, but still in the systematic procedure, how to select the voltage level and number of circuit. Let's proceed for that. Yes, of course, you remember that whatever we are going to discuss, the selection procedure for the voltage and number of circuit is only for the transmission line design. For distribution system, it may vary, and we will discuss that during the distribution system design once we complete the transmission system design. So our new topic for today's class is to select the voltage level and number of circuit for a transmission line. So we have already discussed little bit with you that the criteria for choice of the economical voltage when the power and distance varies. I hope that you remember that, and we also discussed that the economic voltage goes on increasing if the either the power or distance to be transported goes on increasing. Of course, we have not discussed that what is that quantity. So today we are going to discuss what will be that quantity, but the basic philosophy or basic criteria we had discussed. Now, since we have to select the voltage level and number of circuit together, but we have not discussed till now what will be the effect of the number of circuit variation in economic voltage. In fact, in one of the lecture I had started you to derive the expression for the cross sectional area of the conductor required, including the number of circuit, but I thought that that might be the very complex to start with. That's why I derived that expression only for the single circuit. So the basic method to derive that expression is almost the same what was for the single circuit. Just I will give you some steps. Now you can derive yourself. So similarly, as we have derived for the single phase circuit, what you can do is, so suppose you have a transmission line of need to be P power to be transmitted over L distance, only same way as you have derived the expression for P loss. So P loss was I square into R. You have replaced the R. You know how to replace the I. So only difference here I would like to mention you with the multiple circuit is, in previous case this line we had assumed as a single circuit line, of course three phase, but single circuit. But now the multiple circuit, so only the correlation between the P and I will change now, as P is equal to root 3 V I cos phi. That was the expression for single circuit. But if this P is supplied through the multiple circuit, then you may have that this P expression changes to P is equal to number of circuit times the same quantity. So just I will be P upon NC root 3 and V cos phi. Just one NC is coming, put over this in this expression, and you will get the new expression. And then this is of course the power loss for one conductor. So for power loss for all the conductors now also be changing. For previously for three phase, this power loss for all conductor was 3P loss. For the single case circuit, now this will be the total power loss in this case. Total power loss in this case will be 3 into NC into P loss, because this power loss is for each and individual one, only one conductor. So in the three phase single circuit we had three conductors, so that's why the total power loss is 3 power, this expression 3 times of this. And for multiple circuit, if say for example double circuit, then for a case of double circuit you have in total 6 number of conductors. So that's why this per conductor power loss has to be multiplied by the 6. So that is, this will be 3, and this is for double circuit it is 2, and this is the power loss. So if you do the similar procedure, you will find the expression for the power loss in case including the number of circuit as this. As you can remember, if you recall your memory, what we had discussed for the single circuit case, this A and this expression, new expression for the cross section. Of course, I would not, no need to explain now what is this A. This is the cross sectional area of the conductor chosen. So only difference in this equation for case of the single circuit and the multiple circuit is this NC, one new NC is coming, rest everything. So obviously if you put this NC is equal to 1, this expression is exactly the same what we derived for the single circuit case. So as this with the similar assumptions in case of single circuit, here also we can assume with the same, because I am not want to repeat again the same assumptions what we have done. So this A with the multiple circuit can be expressed as K times power to be transmitted to the length up to which it is going to transmit it, divided by the number of circuit times B square. Only again I repeat, in this expression also the only change is this new term is this number of circuit. So now come again for the conductor cost. So just compare the cost in total for the single circuit, multiple circuit. So the expressions for the cross-sectional area now for the single circuit we had derived last time is this. For today, this is this. Only for this is for the multiple circuit. As you know, the number of circuit, number of conductor in case of single circuit is 3, and for the multiple circuit we have 3 into and see 3 times of number of circuits. So for example, for double circuit, this will be the 6. So if you find out the cost of the conductor, this is of conductor, cost of conductor per unit length, then of course it is proportional to, as I have told you, that the cross in the last time also, that this cross sectional area of the conductor is the indicative of the cost of conductor per unit length, because larger will be the conductor size, your cost per unit length will be larger, smaller it will be smaller. And in fact if you multiply the density of this material to this A, this is nothing but the um, weight of the conductor required per unit length, because cross sectional area is also the volume per unit length, right? So the cost per conductor will be just the proportional to this times the total number of conductor. So that's why this will be multiplied by 3. Since this is proportional, that's why this K1 is just saying that this will be the proportional to this quantity, but this K1 may not be exactly whatever is this constant K. So here K1 times 3A for single circuit, and K1, and of course in multiple circuit we have the number of conductors is this much, so that's why this into this. So this is the, and this is the proportionality constant, this K is changing to K1. So here very interesting, if you do this, just do this, what we will find here is it will be K1 times 3 into PL by VA square for single circuit. And for this also you will get that this K1 times 3 times the power to be transmitted to the distance to be transmitted into, sorry, one NC has been here, I can put 3 times number of circuit times not this A is PL upon NC into V square. Yes, of course K is there, so you can put even the K, no matter this K. Now you can see that this NC and this NC will cancel to each other, and of course we will get that now this quantity is K1 into K, say some another constant, so this is K2 and including 3, K2 into PL by V square here, where this K2 includes all these quantity. This is the K2, just indicating that is proportional, not exact value, just for K1, K2 and others. Similarly here, this quantity will be the K2 into PL by V square. So very interestingly, what we have found that the cost of conductor per unit length as a function of voltage is almost independent of the number of circuit. Why I have put in the almost? Why not? From this expression, it looks like just I could say that it's independent of the number of circuit. But here I have said just almost because this expression is indicative of the conductor volume or conductor total conductor volume or conductor weight required. But as you can see, say that for the same weight of the material, if you construct the 3 conductor and 6 conductor, some construction cost will be bit higher. That's why this is almost. So now, if we plot even for the multiple circuit as for the single phase case, single circuit case, uh, the cost of conductor will be like in the previous case. So this is the voltage and this is the cost per unit length. Of course, this is for conductor cost. So whether it is, this is independent of number of circuits. So this is for valid for a fixed P and L, but for any number of circuit. So next question is, what will be the cost if you go for the multiple circuit as a function of voltage? So suppose that you have a 132 kV single circuit. 132 kV single circuit, it has a cost of certain X per unit length, right? Now you have 132 kV double circuit. Do you think that that cost per unit length will be the X or will be higher or lower? In my opinion, it will be higher if for the double circuit. So the insulator cost for the single circuit, as we had discussed, this is the insulator cost for single circuit. Then for the multiple circuit, it may be something like that. So this is the insulator cost for NC number of circuit. Obviously, now you can find that what will be the change in the economic voltage. Previously, for single circuit, the total cost would have been this plus this. So something this will be look like this, right? Now for this will be something look like this. So the economic voltage now has been shifted. And what you are seeing, the effect of number of circuit in the economical voltage, this will be the V economical, say this is for NC1 and this is NC2. Then this is for NC1 and this is the economical, V economical for NC2, provided NC2 is greater than NC1. So a very important conclusion we are getting that if we increase the number of circuits, then for a given amount of power to be given, power to be transmitted over the given distance, that means rest everything is same. But if you increase the number of circuit, then the most economical voltage is decreasing. One thing you must remember at this point, you might be confused with this sentence and whatever is coming here. So no need to be confused. What I have told you is, here it says that the cost of conductor per unit length is independent of the variation in the voltage. But this is the conductor cost at this point, the conductor cost at the economical voltage. So what does it mean that if you go for the multiple circuit, then at the voltage of economical voltage, most economical voltage, the with increase in the number of circuit, the conductor cost is higher than when the number of circuit was less. This, because at the same voltage it is not varying. So since the voltage has been changed, the conductor cost will be changed. Of course, it is very obvious that you have to transmit the same power and you are reducing the voltage. That means the current carried by the conductor in total will be higher. The only difference in the with the multiple circuit or double circuit will be previously it was divided in the 3 conductor. Now it will be dividing into 6. So total current increases. So that's why the total conductor cost will increase. Okay. Now the same thing I have here formally I have put it in the I have plotted this just yesterday with the help of Excel. So here you can see that for NC1, if this is the and what is the economic, we are saying the VENC1 is the economical voltage for NC1 number of circuit, and this is for economical voltage for V economical for NC2 circuit. Yes, you must remember that this NC2 in this is greater than NC1. So if I summarize now, since the cross-sectional area of the conductor, as you remember, in general is expressed like this. So if I summarize, and if you recall your previous memory as well, then what we can say that the effect, just I want to summarize in this table, the effect of economical voltage choice depends on the power to be transmitted, length, and the number of circuit. Then you can say that with increase in the power, the economical voltage is increasing. With increase in the line length to be transmitted, the economical voltage is increasing. However, with increase in the number of circuit, the this economical voltage is decreasing. I hope that this we have discussed so many times that now you don't have any confusion understanding this. Okay, so let's move to how we proceed for the economical voltage choice. So there are some rule of thumbs used by the different utilities to choose the economical voltage. So very simplest one, and but is very indicative, that just use 1 kV per megawatt. What does it mean? That suppose you have 100 megawatt to be transmitted, then this rule of thumb says that you will have the voltage something, transmission voltage something around 100 kV. So that means, for example, 100 megawatt, your transmission voltage may be somewhere around 100 kV. But in this method, the method lacks of considering the line length and number of circuit into account. But I will tell you that even this rule of thumb is a very indicative. You can get the idea just few minutes later. Then the second method, which is also popular by some utilities, that they calculate as the, since in the first method we discussed that it has the drawback of not considering the line length and number of circuit. So the second method, second rule of thumb says that yes, we consider the line length also, and the voltage in kV is just the square root of P to be transmitted and L. If we put P in megawatt and this L in kilometer, then this kV, and of course, as you have seen that both of these rule of thumb have not violated what we had discussed so far. Both of the methods says that first method, since only depends on P, so they say that the economical voltage will increase as the power to be transmitted increase. The second method says that if your either the power is to be transmitted is increasing or the length to be transmitted is increasing, the economical voltage is also increasing. But again, this method, the second method, lacks the consideration of um, number of circuit. So very much popular and are used by, especially for the beginners like you, the most economical empirical formula they use is this. Here you can see that this empirical formula use all the quantity we have discussed, the P, the length to be transmitted, number of circuit. Even this method consider the cos phi. Now we had assumed that this cos phi, the power factor for the transmission line, is very high, but they include this in this equation. So if you include it, no problem, it will very, since the cos phi itself varies in the very narrow range, so the effect, its impact on the economical voltage will also be high. Now you may ask me a question that you have explained me so much about the economical voltage, but these formulas are very simple and very roughly we are calculating. Why it is? Why we are not deriving some expression again for the economical voltage? Just idea we have used for the economical voltage. The answer for this is, just if you get the accuracy of this formula is not very important. I will say now you. Why? Because suppose you are getting from here for a given set of P to be transmitted, a length to be transmitted, and number of circuit, cos phi, each and everything you have. And now suppose you have calculated this as 100.56 kV, right? Suppose you have calculated for a set of, it's possible. Now, are you going to use this voltage? No, I cannot use it 100.56 kV transmission line. Yes. Why? Because what I mean is this, whatever economical voltage we are calculating, it's just an idea. It's something near about the economical voltage, because we are not going to use this voltage exactly. Rather, we are using a voltage which is nearby this, of course, but standard voltage, and that standard voltage also mandatorily should satisfy the technical requirement. Why we choose only the standard voltage? Why we cannot transmit at 100.56? Just I will answer you in two steps. If you just think, just recall your memory, and if you see the different voltage levels used either for the transmission or distribution, I hope that you might have some idea about the what are the voltage levels we are using. Just recall your memory, and what you will get that these voltage levels are 11 kV, right? 11 kV, 33 kV, okay, 66 kV, 66 kV, 132 kV, 220 kV, right? If you just go on looking all these, I, I see one peculiarities on all this. Whether do you observe it or not, I'm not sure, but I can see one peculiarities in all these voltages, and that is all these voltages are the multiple of 1.1. All the voltages. This is 1.1. Sorry. This is also 1.1. This is also, this is also. If you divide it by, you will get an integer number. All this quantity by 1.1. Why so? I hope that in the very first year of your electrical engineering, or even in +2, you might have calculated one factor which is equal to 1.1 for a sinusoidal wave. For a sinusoidal AC wave, this 1.1 is nothing but called form factor. Form factor, which is VRMS or IRMS upon V average. So, as you have discussed, that in the for the optimum transmission and distribution of the electrical energy, we require to have a different voltage levels in in the power delivery system, and that voltage has to be changed repeatedly many times, and the change in these voltages are being done by the transformers. So in the very beginning of the, or in the when the development of the transformer were thought, then it was thought initially that the transformer cannot work if its voltage in the either in the primary or the secondary will not be the multiple of 1.1. But later on it was proved that it was only the myth. This was not the true. the, the transformer can change any voltage level. So as you can also think that with the evolution of the power system, we were not at the same level of voltage level, highest voltage level, same level of complexity. We have not come in a single day. It took that, of course, the demand of the electrical power goes on increasing and increasing, went on increasing and increasing with time. So initially we required lesser power, so lesser voltage. Then we moved for this, then from this to this. In fact, in the very first Thomas Edison electricity, it was operating only at the utilization voltage. So what I mean that, so when it was proved that this form requirement of this multiple of this form factor in the voltage level is a myth, by that time some countries has already adopted up to 220 kV. But later on, once this has been proved as a myth, then that's why you can see that above this voltage level, now we do not have necessarily as a multiple of 1.1. For example, 400 kV. This is a popular voltage. And in our country also, we are constructing some lines in Nepal as 400 kV, which is not a multiple of 1.1. Or some countries are adopting now even 500 kV. Like in Japan, they have 500 kV line. So this 500 kV line is not a multiple of 1.1. Or some countries are adopting 750 kV, or some country adopting 765 kV, or even 1000 kV, or 1200 kV. So maximum voltage till date is up to 1200 kV. So what I mean that above the 220 kV, as you can see, that this rule is not there. So no need of going for the multiple of 1.1. Then this is the first part, that why we should go for the extender voltage. The second part is, okay, once this myth has been, okay, this fact has been proved as a myth, then what's the problem with going on this? Why not we can use this 100.56 kV? Yes. One thing you might remember, that suppose you have discussed you have studied the course, the electrical machine design. So in that case, you have designed that, if, say for example, transformer. Every time you are going to change your primary and secondary voltage of the transformer, you need a special design. But if you have fixed the primary and secondary voltage, only varying the narrow range of the power for that transformer, then something is ready made. Or say for example, insulator. So insulator you can make for, which completely depends on the voltage. Say you can construct the insulator for 11 kV, or you can construct the uh, insulator for 33 kV or 66 kV. This is fixed. Now if you go for 100 and 0.56, can you get this? No. This is the class of voltage. That's why now even the 100.56, some countries are adopting 110 kV, and some countries are adopting 132 kV. So this is almost the same class. Only what I mean is, if you have follow the standard, then some ready-made design and ready-made equipments you can purchase. But if you go for every time a peculiar voltage, then you need to have a peculiar design, and the equipment cost goes on increasing. You need to do the type test, design, type test, and everything. So, and that's not necessary also, because we can go for some range. And that's why even today, though this 1.1 factor is not there, if each and every country has uses only few selected voltage, and though that is called the standard voltage. So after, that's why even we get now, for example, in our country we are adopting these voltage up to 400 kV now. So you can easily say that once I get this voltage 100.56 as an economical voltage from this expression, we are not going to use this voltage, but we are going to use the 132 kV. So now do you think that these expressions need to have a microscopic accuracy? No. Even it is a rough, no problem. Now, if you have some leisure time, I will give you the set of power and distance to be transmitted, and you can choose these, and you will see that these all these are coming to be very a narrow range difference. And ultimately, we have to go for the standard voltage, and also we need to satisfy the technical requirement. So next job is in the overall steps for the voltage selection is first compute the economical voltage for varying number of circuit. The number of circuits could in general even for 3 or 4, but most common is either for single circuit or double circuit. So just in the beginning you can start with these two. So and find out the V economical 1 and V economical 2. What does it mean? That you have been the given set of P and L, right? So first case, B economical 1 is that given P, L, and the number of circuit as NC1. This economical voltage B economical 2 mean that given again the same P, same L, but with NC equal to 2. So this will give you the some idea. This when you calculate that, it will give you the voltage, sorry, economical voltage. Now choose the nearby standard voltage, that is B standard 1. And now I would like to test your or I can explain you what I mean. That suppose you are adopting 132 kV transmission line till now in our country and 220 kV. Of course, I have told you that if we have calculated say 99.98 as an B standard 2, right? Okay, yeah, B standard 1, B standard, okay, so say B standard 2. Yeah, we have calculated 99.98 kV. Obviously, what will be your choice? The nearby standard voltage, you will choose 132 kV, no doubt at all. Now, suppose B standard 1 is coming as 144.32 kV. This is as B standard 1. What does it B standard 1? B standard 1 is the voltage you are going to choose nearby B economical 1, and B standard 2 is the voltage economical voltage you are choosing for B economical 2. Why I now what you are going to choose? Whether you are going to choose the 132 kV nearby voltage, whether for this voltage standard, this economical calculated voltage, this is B economical. Say I have told you this is 2 and this is B economical 1. So for this there is no dot at all. We are choosing this B standard 1. This is your B standard 2, right? So B economical 2 corresponding B standard 2 is this. Now for V economical 1, now we have calculated this B economical 1, and fortunately or unfortunately it has come as 144.32 kV, for example. Then what will be your V standard 1? I am asking you whether 132 kV or 220 kV. Why I am asking this question is, usually as an electrical engineer, when we go for something related, always in our mind is that whatever we have calculated, and if you need to some standardization or something, we should go for next higher. But here it is not necessary, because it is not the this is not the technical voltage. This 144.32 kb which we have calculated is not the technical requirement, is not a technical voltage calculated. It is just the idea of the economical voltage. So why I have not written here, I have written very clearly not the next standard voltage, but I said the nearby standard voltage. So even for this economical voltage, nearby voltage is this. So this could also be the B standard one. I hope that you have clear what I mean. So this voltage, this B standard voltage 1 and 2 numerically may be same or may be different. Don't worry that it must be the different or it must be always be the same. Just only is calculate these economical voltages, and for each of these economical voltage, choose the nearby standard voltage. Well, it may be same, no problem, no worry. We'll proceed further for the final choice. Now, what you require, you need to check that whatever if will be for the number of circuit case 1 the standard 1, and for the whatever is the standard voltage for this circuit 2, number of circuit 2, both of these need to be passed with the technical requirement. And because this is mandatory especially for long line, and as you know that the transmission lines are usually the longer lines. So for transmission line, always we check for transient stability. Check for, as you can see that for distribution system we may not need to check the transient stability. Why? Because in distribution system the line carries power only for in the proximity of consumers. So that's why in distribution system, line lengths are smaller, whereas for transmission system, line lengths are longer. And as you had discussed, we have discussed in one of the class that this transient stability, it may be the dominating factor. This may be the dominating factor only in case of long length line. So that's why for distribution system, this technical requirement will not be needed. That we will discuss later on, but of course some other criteria. But for transmission lines, since the transmission lines are the long length lines, always we need to check whether the chosen voltage be standard 1 or 2 or even for the circuit 3, whatever standard voltage we are going to choose, we need to check that whether that just qualify for the transient stability or not. How to check that? Very simple. As we have already discussed that the P limit, the, according to the transient stability limit, is varies as V square by L. So one of the option could be that because number of standard voltage is not huge, not infinity, only selected number of standard voltage. So you might have been available as a designer, you will have the data available which says the capability curve, as we have plotted this capability curve as a function of the p limit versus L for each and every standard voltage. Say you might have get this for 66 kV, then you might have got the another curve for 132 kV, and you might have for 220 kV, right? For 400 kV. So you might have the availability of this. Now, in this case, you know what is your distance to be transmitted. So say your distance to be transmitted is this. So say your distance to be transmitted, say, is this. This is your L to be transmitted. L to be transmitted. The power at which distance it is to be transmitted, right? Transmitted. And you also know that what is your power to be transmitted. Now, suppose you have chosen the 132 kV. So, for 132 kV and for this L, the limit of the power, this is the limiting power. This is the limiting power, P limit. So, if your power to be transmitted is, say, for example, here, this amount, that means it passes the technical requirement. But if your power to be transmitted is here, this is power to be transmitted, and this is the P limit. So the very simple is, so one option could be that for each standard voltage, power transfer capability curve, this is the power transfer capability curve, which we had already discussed in one of the class, is simply P limit is proportional to V square, because if you remember that this expression, we had derived this expression from P is equal to V square upon inductive reactance per unit length into the line length into the sign of delta, and we have discussed that since this delta has the limitation due to the transient stability limit, once we put this delta as limit, this P becomes as a limit. And we also discussed that this X is very much constant on vary in very narrow range. The inductance varies around in 1 millihenry range, and this is the 2 pi FL of this inductance. So what we had discussed, that we can say that this P limit is something constant K into V square upon L. So this K includes all the factors we need to consider, and this V square L. So these curves are these are the limiting curves for if it is available. Then you can check that whether the power to be transmitted at given length, this L length, is if it is below the curve, this has passed. If this is your case, it pass. This point pass, but this fails because your power to be transmitted at this for this length is beyond the limiting value for this voltage line at this distance. Of course, what you have to do is either you have to go for the next higher voltage, or you have to increase the number of circuit in that case. This capability curve now also need to be available for varying number of circuit as well. So if we follow this method, for this method, what is required that you should have a number of capability curves available for each standard voltage, for each standard voltage, and possible number of circuit. The capability curve should be available. It's very too many datas. So I am thinking, and not only me, several the designers, the experts are thinking that is it possible that you should minimize this data available? And what they have, this is the same thing what I have explained you. So the another method, what they have thought that, since again I write down here, we had the expression for P limit equals to some constant K times V square by L, right? So another option could be make the capability curve independent of the voltage and number of cells. This is very important. How we can make it? Is it possible? If it is possible to that this capability curve data, of course, is available, but if it will be made independent of the voltage and number of circuit, independent of the voltage and number of circuit, then only one curve will be sufficient for checking purpose. So now I need to explore and to share with you that since this quantity is power, so one thing I in my mind is, if I divide something both sides, numerator and denominator, by v square, then this expression can be made, the right hand side of this expression becomes independent of v square. But since this is PSP power limit, and divided just dividing by voltage square may not be that much meaningful. Secondly, we also need to take care about the number of circuit, and number of circuit is hidden, not written in the expression. So what I mean search is, if I divide both sides of this equation by a power quantity, because both sides of these expressions are the power, that power, the mandatory condition for this dividing the power by which we divide is that power should be proportional to the voltage square, and if possible should also include the information about the number of circuit. Why I am dividing the power with the power both sides? If I divide both sides, then it becomes the unitless. Previously, if you just divide by voltage square, then what will be the unit for this? P upon B square, something like that. It's very complex. So I hope that you remain. If you have been the interactive class, I might have asked you here, do you know such type of any load? But because we are not in interactive, so I will give you myself. How we can do is, I hope that you might be aware about one terms. This is called a surge impedance loading. SIL. Surge impedance loading. What does it mean? That is, what is surge impedance loading? You have a line. It has line impedance itself. You have the source. So surge impedance. This is the I'm making a transmission line model. This is a transmission line model. Transmission line model. So surge impedance loading of a transmission line is simply a load if we connect the load resistance equal to this load resistance equal to the surge impedance of the line, or also known as characteristic impedance of the line. So is known this impedance ZC, either the characteristic impedance or surge impedance. In fact, this surge impedance loading has other technical meanings. For example, if you have studied the Ferenczi effect in the power system, then this is the loading. If a you might have studied it in the Ferenczi effect. We will discuss a little bit more when we select the conductor. Or again, this Ferenczi effect, if you forgot what you have studied in the power system. But I will just give you the conclusion in the Ferenczi effect is, Ferenczi effect says that if the line is lightly loaded, the receiving in voltage may be greater than sending in voltage. And also says that if it is the heavy loaded, transmission line is heavy loaded, the receiving in voltage will be smaller than the sending in voltage. What is that benchmark? I will justify you when discussing the conductor selection and going in bit depth about the Ferenczi effect, that the benchmark for that lightly loaded or heavy loaded line is the surge impedance loading. So it is always true that if the line loading, I'm not deriving this, but just giving you the fact, if the line loading is less than surge impedance, its surge impedance loading is the lightly loaded. We call it as lightly loaded condition. Why? Because if line loading is equal to surge impedance loading, then Vs is equal to Vr. This is the Vs, the sending in voltage. This is Vr. Here we are not using the surge impedance loading to make the sending in voltage to the receiving voltage, but we are just using this terminology, this surge impedance loading. The another important part where this surge impedance loading is becomes very important. I don't know whether you have studied or not. So traveling wave we call. So traveling wave, when you have a wave, high frequency wave travels along the line, high frequency wave travels along the line, the voltage wave or current wave, then once it comes to the end of the line, partial of this wave may be reflected or refracted, and or full of this wave may be completely reflected. So this phenomena, and say for example in case of open circuit, it is said that if the voltage V is reaching at this point, the full is going back because there is no path for going here over here. So the voltage is double. But if it is a short circuit at this point and V voltage wave is coming at this point, then at this point ultimately the negative V will be reflected and the voltage at this point is 0. So it may be vary at this point from 0 to V, 0 to 2V for a traveling wave of V, depending on what is the impedance here. So I have said for example, open circuit, the load impedance in case of open circuit is infinity for open circuit. This load impedance is, oh, sorry, the electricity has gone. बत्ती गएछ, मलाई एक्सप्लेन गर्न अलि गाह्रो भयो है. वाइफाई त मेरो चल्छ, स्लाइडबाट त म एक्सप्लेन गर्न सक्छु, के गरौँ? हेलो हेलो हेलो
हजुर सर.
बत्ती गयो. यो मेरो यो जुन डिजिटल बोर्ड छ नि, त्यो चाहिँ काम न, त्यो चाहिँ डिजिटल बोर्ड चाहिँ काम नगर्ने भयो है. के गरौँ?
स्लाइडबाटै गर्नु सर.
हजुर, स्लाइडबाट गरौँ है. हुन्छ. सो मैले भन्न खोजेको कि यो आइडियाले पनि के देखाउँछ भने कि when the load impedance is infinity, they completely all the wave is traveling back, that is full reflection. Where the load impedance ZL is 0, then there is no reflection at all. So that means there may be a condition of the impedance in between that, and you can again just verify that if this load impedance is equal to the characteristic impedance, then the reflection and reflection both are not at all, and the receiving in, when this V voltage will reach at the receiving end, it will remain intact at B voltage. So these are the two major application of the surge impedance loading. But here we are going to use the surge impedance loading just as a dividing factor for this P limit, so that we can make. Hello, hello, yes, just as a dividing factor. So if you divide this P limit by a power which is proportional to the square of the voltage but independent of, yes, one very important factor about the surge impedance is it is independent of the line length. This ZC is equal to divided by square root of Z by Y, and for lossless line this Z by Y square root converting to square root of L by C. So L, whether you put for the full line length inductance or per unit length, only mandatory condition is if you put the numerator for full length, denominator also for full length. So if L is for full length, C also for full length, and if L is per unit length, the C also should be per unit length. So root under L by C is the characteristic impedance which is independent of the line length. So once the surge impedance is independent of the line length, obviously the surge impedance will be independent of the line length. Now, whether the surge impedance loading depends on other factors. So if you just see what is the surge impedance loading is, uh, surge impedance is Z upon C, and I have told you, if you remember, that since the both the inductance, as we had discussed that, especially for case of inductance, the inductance that is expressed in terms of logarithm of GMD upon GMR, right? And I have told you that the variation in the GMD upon GMR is from 400 to 1200, and because of that, inductance per unit length of a line is almost virtually constant. Similar thing you can expect for the capacitance as well, isn't it? Because the capacitance expression is also 2 pi epsilon divided by ln GMD upon GMR. Here the varying quantity is only the GMD upon GMR, and if the GMD upon GMR varies in a from 400 to 1200, again like in the case for uh, inductance, then the capacitance per unit length also varies in very narrow range. So what I mean is, if you calculate, I can calculate, but because of the unavailability of this digital board, I am just explaining orally that if you calculate for a practical line square root of its inductance per unit length by the capacitance per unit length, you will get that this varies very in the narrow range around 400. So in minimum case you may get 380, or in maximum case you may get 410 or 15 or 20, something like that. So virtually, for like I have told you in the last class, that one of the last class, that if you don't have any information regarding the inductance of the line, you can assume around 1 millihenry per kilometer. Similarly, if you have no any information about the inductance, capacitance, line configuration, conductor size or something, you can assume that the line surge impedance is about 400 ohm per kilo. No per kilometer. It is for full line. So of course this is the very important question usually asked in the competitive exam as well. That if the 400, if for a 100 kilometer line surge impedance is 400 ohm, what will be for 200 ohm? So in fact, it is independent because it is a ratio of inductance and capacitance. So that's why the surge impedance is independent of the line length, and it is around 400 ohm for single circuit. What will be the for double circuit? Obviously, these two lines are connected in parallel in case of double circuit. So for double circuit, the surge impedance is 200 ohm. So now, if we divide this P limit expressions, I have written you earlier, as P limit divided by the K times is equal to K times V square by L, then divide both sides by the surge impedance loading, and you will get that this expression as I have expressed in this below this green line, that is K times ZC, where ZC is the characteristic impedance or surge impedance of the line divided by the line length. This characteristic impedance, yeah, as it is almost constant, so you can say that this MF limit, that is this is the multiplying factor limit. What is this multiplying factor limit? It is the ratio of P limit, that is capability of the power to be transferred, P limit, to the surge impedance loading. Since this is constant, so you can say that this MF limit is just only depends on as and inversely proportional to the line length. So since the surge impedance is almost constant, ZC, as I've given, its value to a single circuit is 400 ohm. That means this MF limit, whatever is calculated in above, is inversely proportional to the line length only. And this data usually, now previously you had seen that you may require the capability curve for each and every voltage level for each and every set of number of circuit. But now if the capability curve, single capability curve, can give the limiting value of power transfer limit at for any voltage level, or and so for example, say you have a 132 kV, and what will be the power transfer limit at 160 kilometer. Just see the at 160 kilometer, see what is the capability multiplying factor limit value, and multiply that by the one surge impedance loading of 132 kilometer 132 kV line. For that, you need to calculate the surge impedance loading for any line, and I hope that now you might have understand how to calculate the. So in numerical data, we'll use the for the this is called capability curve, and this data we'll use throughout this design, whatever is given here in the table. And in fact, the above line I have plotted just from this table itself. Okay, so now with multiplying factor, how we can use again to check the technical requirement. So what you can do is, for the choosing, now we had all I had already explained you what is V standard 1 and what is V standard 2. V standard 1 is the economical voltage corresponding to standard voltage very nearby the economical voltage calculated for circuit 1, number of circuit 1, and V standard 2 is the standard voltage you chosen very near to the economical voltage computed for double circuit. So we can calculate the surge impedance loading for single standard 1 voltage and standard 2 voltage like this. For single circuit, the surge impedance is 400 ohm, and for double circuit it is 200 ohm. So this way you can calculate. For example, for 132 kV, now you can calculate the surge impedance loading for any voltage level. So immediately if I ask you what is the surge impedance loading for 132 kV, simply you will do that 132 kV square. And one thing very important, that if you put in this expression the voltage in kV, line to line kV, it will give you the 3-phase megawatt power directly. So you no need to use the unit conversion. So for example, for 400 kV line, the surge impedance loading is 400 square divided by 400. So that is 400 megawatt. So it is a three-phase power. So it's because we have used the line-to-line voltage. So root 3 phase, and just you multiply it, root 3 square becomes 3 itself. So it will be, it is in fact either saying BLL square or 3B phase square is the same thing. And if you use in kilovolt, then you will get directly in the megawatt answer. Okay, so we will have B standard 2. Okay, can you see whatever I'm writing here? देखिए आपने बात समझ लिखे को?
Yes, sir. Yes, sir.
Yes, so power has come. So just what I mean that for 132 kV line, the surge impedance loading is 132 square upon 400 for single circuit. But for double circuit, it will be divided by 200 because the two lines are in double circuit is nothing but is a two single circuit lines are in parallel. Okay, so this is the first point. We calculate the surge impedance loading. Next, what you can do is you can compute the your power to be transmitted. P is not, and you have the surge impedance loading. So you can check the multiplying factor. You can calculate for your power to be transmitted. So that will be the P to be transmitted divided by the surge impedance loading, which have been calculated just in the above step. Now, instead of checking P, what you can, so here I draw again. So you have the MF limit. MF limit is curve is one curve is here, and now you have your multiplying factor for your given power to be transmitted. This is your given power. So now just check that whether your for a given distance, whatever is the distance your power P has to be transmitted, just check whether this MF calculated in step 2 is below this MF limit curve or not. If it is below, yes, it is capable. If not, if it is above this curve, that means it is not capable. Now, either you can use this, or ultimately you can do is by calculating this, you can convert your MF limit curve itself in terms of directly in terms of capability. Now, if yes, it is satisfied. If not, no. Now, one thing could happen is now you have two standard voltage, right? For two economical voltage for the number of circuit 1 and number of circuit 2. So it could happen that either one of these. What does it mean? I say that you have some say 100 megawatt to be power to be transmitted, say over 100 kilometers or 110 kilometers. So this was your input. From here, what you have calculated is you have calculated the B economical for number of circuit 1 or number of circuit 2. Now you have chosen the standard voltage for number of circuit 1 and number of circuit 2. Say for in both the cases it might be 132 kV, 132 kV in both the cases. Not necessarily always it will be the same, but for this case, if it's say for both case, now it could happen that since the multiplying here the surge impedance loading say for and this case, what is the surge impedance loading for this case is 132 square upon 400. Here for this case the surge impedance is 132 square upon 200, right? So 200. So I guess that it will be something around 43 megawatt or something there. And I'm not sure, but something around. And it is so popular that people usually remember it. And therefore, this will be around 86. So for this case, you can see that if you go for the single circuit, your MF, your MF will be just from this, and this you can calculate. MF for single circuit will be 100 divided by yes Okay, 100 divided by 43, and MF2 will be 100 divided by 86, right? So 100 divided by 43 is around 2.2 or something like this, right? I'm not putting these with calculation. Don't think that I have a calculator here. I'm just writing that something it will be 100 divided by 43, I guess, is around 2.23 or something like that. And this will be around 1.15. Okay. So just go back. So you have two multiplying factor calculated in a step 2. One is 2.3 and another is 1.15. Just remember these two. For single circuit, our multiplying factor for the power to be transmitted is 2.3, and for double circuit it is 1.15. Now if you go back and just capability MF limit curve, so from the curve, what was your MF1? MF1 in the next previous case, MF1 was 2.3 and MF2 was 1.15. And I had said you that our distance to be transmitted is somewhere here around 110 kilometer. So MF, if for the single circuit case, it is 2.3, right? 2.3, 2.3, it will be somewhere 2.2, 2.4. So it is around here 2.3 for an MF equal to. So for single circuit, MF1 is here. And for double circuit, it is much below. This is for the double circuit, MF2. So here you can see that almost for this case, if 100 megawatt is to be transmitted for 110 kilometer, both are satisfying. Both are satisfying. This is also satisfied. This is also, this multiplying factor MF1 is also below this curve, and this MF2 is also below this curve. But what could have been if this line was say 240 kilometers? So if the line length, this 100 megawatt, if that 100 megawatt again has to be transmitted over the distance of 140 kilometer, 240 kilometer, then you can see that the again your MF1 would have been here and MF2 would have been somewhere again here. So this is for, this is the case for, this was the case for line length 110 kilometer, and this is the case for line length 240 kilometer. Now you can see that this signal circuit case is violating the limit. So only the double circuit, this is pass, this is fail, right? Now if your line length would have been say something around 500 kilometers, something around 500 kilometers, then you can see that both could have been the fail. Both would have been the fail. This is also fail. This is also fail. So this as I have summarized here. So it is possible that for, as we have calculated the this multiplying factor and so checked for the stability, out of these two, V standard 1 and V standard 2, one could be, only one can be pass, another one could fail, or both of these could pass, or none of these could pass. I hope that you must be very happy for, as for your level as a student, that if this would have been the case, we do not have the burden, because we have calculated two standard voltage. We have to finally choose one amount, one between these two, and one passed the technical requirement and then one another is failed. So it will be very happy. We, for example, case of the second case I have told you, that is 100 megawatt for the 240 kilometer. Then what would have been that we had 132 kV single circuit, and we had 132 kV double circuit, and we found that this does not comply, not comply, not comply the technical requirement. It comply with the technical requirement. So it was very easy. If this would have been the case, it would have been the very easy to choose 132 kV double circuit for 100 to 40 kilometer. But like in this case, in case of 100 megawatt for 100 kilometer, 110 kilometer, you have seen that both of these options, both were passed. Now you cannot use both. Finally you have to select one among these. So what we have to do, that is a burden that you may need to make some, explore some other parameters. And if none of them, then what we do? So what I mean that it could happen that multiplying whatever we have chosen the two standard voltage, both could, a number of circuit combination, both, if only one of these pass and one fail, that means just select one, your voltage selection and number of circuit has completed. But if both of these comply the technical requirement, or none of them comply the technical requirement, then what to do? We will discuss this in next class. Okay, so with this today I would like to stop here. के छ तपाईहरु, हामी चाहिँ धेरै फास्ट भयौं, धेरै स्लो भयौं, टिक्क भयौं, के छ यो फिडब्याक? बिकज मलाई पनि यो